Yo, welcome back. We are going to talk about the symmetric definition of the derivative. But before we do that, let's refresh our memory on the definition of the derivative. So remember, I got two things going on here. I have this red line, which is going to be my secant line, and I have this green line representing a tangent line. I'll call this point x, and what we do is we say, all right, we're interested in the slope of the tangent line at x. So let's take a look at this point at x, but then also some later point. We'll call it x plus h, where in this picture h is drawn to be positive. And we're going to start by finding the slope of that red line. Well, all right, what would the y value here be? Well, it'd just be f of that, so it's just f of x. What would the y value at this point be? Well, it would just be f of that. It'd just be f of x plus h. So the slope of the secant line is the delta y's over delta x's, right? It's going to be f of x plus h minus f of x all over what you get when you do x plus h minus x. But the x's would cancel, sum to zero, you're just going to get h. So this represents the slope of that red secant line. It's also known as the average rate of change of this function over this interval. So now to get the slope of the tangent line, we simply take the limit of this difference quotient, the limit of f of x plus h minus f of x all over h, as h goes to zero. And what that'll get us is the slope of the tangent line, but at x. So I'll answer will have an x in it, so we will get the derivative, right? F prime of x, that slope producing machine. So if we wanted to visually see this, think about it, right? If h is going to zero, this point, right, is going to get closer and closer to this point, right? The smaller I make h, the closer the points get to each other. And what do you see happening? You see that secant line slowly becoming or occupying that limiting position of the tangent line. And the smaller I make h, the better my approximation would be, right? And if I take the limit as h goes to zero, then I end up getting the slope of the tangent line. Now, I drew the picture for h being positive. So in other words, when I show you this little visual here, this is taking the limit as h goes to zero from the right? H being positive, getting closer to zero from the right. But remember, limits are a two-sided idea, and this is going to start to come into play in the next lesson. So I could also draw the picture, right? Like I could have labeled this point x plus h over here, where h now is negative. So now h is going to zero from the left, right? So h is small negative values. And as I approach zero from the left, you see I approach the same thing. So this would be an example of the limit as h goes to zero from the left. You see that secant line occupying that limiting position of the tangent line. And this is an example of the secant line coming from the right. That is our definition of the derivative. This is the definition of the derivative. You need to know that. All right, so now what is this symmetric definition of the derivative all about? Well, let's take a look at this picture here. All right, and maybe before I put some numbers on there, I'll turn them off. So what's going on here? Well, let me label this very similarly. All right, so here we go. I'm going to say I'm interested in finding the slope of the tangent line, which happens to be purple now, at x. All right, so here's my x right here. This point, I'm going to do something very similar as I did before. I'm going to say it's some later point, x plus h, where this is obviously h being positive, right? And then I'm going to say, you know what? Not only do I want to represent x plus h, but I'm going to be symmetric here. And I also want to look at x minus h. So this point right here, so kind of looks like it's coinciding with where that tangent line hits the x-axis, but it's not. It has nothing to do with that. So this point right here is x minus h. So I start with x, I add h, and I subtract h, and I get these two new x values. So now what would the y value here be? Well, it would be f of this. It would be f of x minus h. What would the y value here be? Well, it would be f of that. It would be f of x plus h. So watch what we're going to do here. We start the same way. This green line is the secant line. So I'm going to start with finding the slope of the secant line. So it's delta y over delta x, right? It's changing y's over changing x's. So now it's going to be f of x plus h, that's this y value, minus f of x minus h, that's that y value, all over what I get when I subtract the two x values. So x plus h minus parentheses, x minus h, right? I need those parentheses now because this is a binomial. So now if I spruce this, I'm going to get f of x plus h minus f of x minus h, and then over When I distribute the negative, the x and the negative x will sum to 0, minus h is plus h. I'm going to get 2h down here. So this represents the slope of that green secant line, or the average rate of change of the function over the interval, in this case, x minus h to x plus h. So how do I get the slope of the purple tangent line? Well, very similar to what we did before. It's the limit as h goes to 0 of this new difference quotient, f of x plus h minus f of x minus h, all over 2h, right? That gets me the slope of the tangent line at a general point x. And so since I'm putting x in it, not a value like 7 or 2 or 3, I'm going to get an answer in terms of x. I'm going to get a function. That function is going to represent the derivative, the slope producing machine. But take a look at how this plays out when we visualize it. So as I make h get smaller, right, what's going to happen to both of these points? Right? So if h gets smaller, that means that x plus h is going to be closer to x, and x minus h is going to be the same distance, just on the left side closer to x, right? So you can see as I make h smaller, my secant line does something a little different than what the other definition was doing, but it still gets closer and closer and closer to that limiting position of the tangent line, right? So for large values of h in the symmetric definition, that's what the slope looks like. But as I bring it in, you can see it actually looks like they're almost parallel pretty closely, right? It almost feels like it approximates it better as we get closer and closer and closer. But then it doesn't matter about approximation. If you take the limit as h goes to 0, you're still going to get that slope of that tangent line right there. So now, why am I showing you this? There's a really good chance that you're not going to see this on the AP exam. So why is it that I would want to show you this new definition of the derivative, rightfully named the symmetric definition of the derivative? Well, I'll tell you why, all right? So let's do this. Let's actually put some axis numbers on here. And let me show you what's going on in that this is the graph. The red thing is the graph of the function ln of x, all right? And 2 is where I want the slope of the tangent line. And you can see what's happening now, right? You see the actual function. I'm showing you this because this, believe it or not, is what your calculator does. What do you mean? What does my calculator do? Your calculator doesn't take a limit. It doesn't have that ability. But what it will do is it will plug a very small value in for h. And you can see as I make h smaller and smaller and smaller, the slope of that secant line gets closer to the slope of the tangent line. In fact, I believe, although this might be updated since, but it used to be, and still think it is, the calculator actually plugs in 0.001 into the calculator. So now take a look at that. You can't even see the difference between the secant line and the tangent line. They're so close. So now, what do I mean that it's plugging that in? So it doesn't do the limit. It just does the difference quotient. So for example, right, this is 2, then 2 plus h, I can't even draw it here. It'd be like 2.001, right? So 2.001, and then the other side, 2 minus h is 2 minus 0.001, so 1.999. So what it basically does is f of the 2 plus h, the 2.001, minus f of 1.999 all over what I get when I subtract these. So 2.001 minus 1.999. I guess I'll write it this way just so you see it as the average rate of change, but that's just going to be 0.002. That's just 2h, right? So this is the slope of the secant line. This is actually what your calculator does. Notice there's no limit here. It's not taking the limit. It's just plugging in a very small value of h. So it's actually giving you a slope of a tangent line. So you can see I actually had Desmos do it for us right here, where the a value being plugged in right now is 2 and the h value being plugged in right now is 0.01. You can see that it's telling me the slope is 0.5 point a bunch of zeros and then this stuff right here, right? So that's what it's the estimation for that slope of that tangent line is. So again, why am we doing this? Because it's what your calculator does. So if I come over to your calculator, when I say your calculator, I mean the TI-84. If I in y equals put ln of x, right? And I'm going to quit out of this now. I'm going to go math 8, remember? That's how your calculator finds derivatives at points. The derivative with respect to x, since I put it in y1, I'm just going to do vars, y vars function, y1. And then I chuck in 2 here. And you can see, oh, look at that. That's like the same decimal that I just got when I did it in decimals, 0.5, a bunch of zeros, and 417. If we wanted to go crazy, we can even see it, and maybe this will drive it home, by actually calculating the slope of the secant line. So let me do parenthesis, because I'm going to wrap up the entire numerator. I'm going to do the function evaluated at 2.001. Oop, I put too many zeros in there. 2.001. All right, minus the function evaluated at 1.999. Close that, close the numerator, and then divide it can't speak, by 2.001 minus 1.999. That's basically the slope of the secant line. Bam! You can see it's giving you the same thing. All right? So I wouldn't be able to sleep at night if I didn't show you that that's actually what your calculator is doing. So it doesn't really give you the exact value, but for all intents and purposes, it's going to be usually pretty accurate, definitely accurate to 3 decimal places. So that's what's going on. So hopefully that made your day. It made my day. That's the symmetric definition of the derivative, and your TI-84 Plus, that's the one it uses. Be good.